Thanks FlexSeal for sponsoring this video and powering our science mission. Hi, I'm Mark from Team Dominator. Project Skyfall is our airborne sensor, and in 2019 we launched it into the Lawrence Linwood EF4 Tornado. We have three ways we can deploy the sensor. The primary deployment method is by rocket, where we launch the rocket directly into the tornado. We can also launch by air cannon, where we fire the sensor up to about 1,000 feet into the tornado. And if we're launching into a tornado-warned supercell, then we can launch by balloon. This video is discussing the balloon launches and how we do that. Every deployment has a purpose, and for this mission we're going to be testing flex tape at very cold temperatures and high altitude, and we're also going to add a camera to the flight so that we can see video from the balloon. Here's the sensor we're launching. We're encasing it in foam because we could reach temperatures down to about -100 Fahrenheit, and we need to keep it warm. To launch a weather balloon, you need a gas lighter than air. Typically this is hydrogen or helium. Hydrogen is a highly flammable gas, and one spark or small mistake can end up with an explosion. Learning from history, the Hindenburg airship was filled with hydrogen, and we know that that exploded, so we use helium. We built the Skyfall sensors ourselves, and we designed them to be extremely small and lightweight. This nets us a major advantage over regular meteorological balloon launchers. Helium is a limited and costly resource. We use about 1/20th of the helium used by a regular balloon. Also, because our payload weight is less than that of a small bird, we're not a threat to aviation. This is our launch setup, which we use for rocket, air cannon and balloon launches. We use an iPad to track the sensors in real time using custom design software. In the Black Pelican we have equipment for balloon launchers. Sensor payloads ready to go, just pull the tab on the battery. A supply of balloons, we have 8 in here. A handheld tracker if we need to recover on foot. Tape for sealing the payload and the balloon, and a piece of ribbon to fill the balloon to the correct size. In the yellow Pelican we have the magnetic antenna to mount on the roof of the vehicle, the receiver, and a Wi-Fi hub. The antenna is omnidirectional. The wind today is 35 miles per hour. The bigger the balloon gets, the more difficult it is to control during filling, especially when it's windy. This is another advantage of having a small payload and a small balloon. I'm testing flex tape to seal the balloon nozzle to make sure that no helium leaks out. And then it's launch time. Launching in high winds like this is good practice for severe weather. The balloon is moving at 35 miles an hour and is ascending at 5 miles per hour. Time to get back into the chase vehicle to catch up. We track Skyfall remotely, and we know where it is at any point in time. We get updates every second. Usually we recover the sensor too, in which case we get access to data that's 10 times per second when we download data directly from the sensor. The information shows everything we need to follow the sensor effectively. On the map, the blue dot is where the vehicle is, and the red marker is where the sensor is. We can tell the balloon's altitude, whether it's going up or down, and the speed it's moving and the direction. Also, it gives us a bearing and distance to intercept from the vehicle. We also have a second display we can use if we want to see what the sensors are doing over time. As the balloon rises, the air pressure decreases and the volume of gas inside the balloon expands. Eventually the balloon will burst and the sensor will return to ground. In the thin air, the sensor falls fast, and as the air thickens up, it slows down. Red on the ascent speed line indicates that the balloon is now burst and it's falling. Time to catch up with the sensor. With the system we've created, I was able to time the intercept perfectly and the sensor fell out of the sky as I was pulling up. A short stroll in and I was able to recover the sensor. And it was just in time for sunset. The distance travelled was 18 miles, we reached 34,300 feet and the flight time was 1 hour and 21 minutes. The highest wind speeds were at the surface. Here's the track of the flight. Note the long track at the start, which are the fast surface winds. And at the top there's a reversal in wind direction. Here's the flight data. So how did the flex tape hold up on the nozzle? Ascent speed was constant at around 2.3 meters per second, so there were no leaks from flex tape. Also, the camera is still perfectly attached on landing. The balloon reached 34,300 feet and minus 63 Fahrenheit. Flex tape performed well. We're going to be using it for future launches. Also, we got video from the camera and it looks just like Google Maps. You can also see the clouds below. Thanks for listening and thank you to Flex Seal for sponsoring this video. Flex on.